Finding the radius and interval of convergence of a power series. A power series centered at x equals a is an infinite series of the form the sum of n equals 0 to infinity of c sub n times the quantity x minus a to the n. And if we expand that out, we would get c sub 0 plus c sub 1 times x minus a to the first plus c sub 2 times x minus a squared plus and so on with the general term as c sub n times quantity x minus a to the n. The index can start at any positive integer. Informally, we can think about a power series as an infinite series that is also a function of x. When students first start learning about infinite series, they get confused as to why they have to learn all of these tests for when an infinite series converges or diverges. Well, it helps us with this big picture goal, which is to determine the radius and interval of convergence for a power series that has the form the sum of n equals 0 to infinity of c sub n times the quantity x minus a to the n. And let's go ahead and recall that informally, the interval of convergence is the set of x values that make the power series converge to a real number. And the radius of convergence tells you how far you can move away from the center before the power series stops converging. Finding the radius and interval of convergence for a power series can be broken down into two separate types. First, if C sub n is constant, we have a geometric power series and can find the radius of convergence and the complete interval of convergence. But if C sub n is a function of n, so this piece in front, if it's not just a constant value, it's a function of n, we're going to have to apply the ratio or root test to find the radius of convergence. To find the complete interval of convergence, we must test the endpoints for convergence as well. So we're going to look at some examples of both. In this example, we want to find the radius and interval of convergence of the sum of n equals 0 to infinity of the quantity x minus 3 over 2 to the n. Now this one is a geometric power series. So in front of the x minus a to the n is just a constant 1. So what's in front here is not a function of n. So because this is a geometric power series, we know that a geometric series converges if the absolute value of r is less than 1. So this piece right here is my r value. So what we're going to do is we're going to solve when the absolute value of x minus 3 over 2 is less than 1. Because again, we know that a geometric power series converges when the absolute value of r is less than 1. Let's go ahead and factor out the 1/2. So we have 1/2, the absolute value of x minus 3 is less than 1. And then let's go ahead and multiply by 2. So we have absolute value of x minus 3 is less than 2. Now I'm going to pause right here. Once we get to the absolute value of 1x minus 3 is less than a number, that number on the right-hand side is the radius of convergence. So once we get to that x minus a in absolute values is less than r, that number on the right-hand side is r. So right here, I can go ahead and say the radius of convergence is 2. But now, because this is geometric, I can finish out the problem and find the full interval of convergence. So I'm going to go ahead and create a 3-part inequality here to drop the absolute value bars. So we know -2 is less than x minus 3 is less than 2. And then we'll add 3 to all 3 parts of the inequality. And we'll get 1 is less than x is less than 5. So this is my full interval of convergence. It does not include the endpoints because we know for a geometric series, we needed to solve when the absolute value of r is strictly less than 1. If the absolute value of r is greater than 1 or equal to 1, then the geometric series diverges. So these endpoints are not included. So the interval of convergence is 1 is less than x is less than 5, Or if we want to write it in interval notation, we'd use parentheses, 1 comma 5 parentheses, so open parentheses on both sides. Let's find the radius and interval of convergence of the sum of n equals 1 to infinity of n over 2 to the n times the quantity x minus 3 to the n minus 1. So this is not a geometric power series. So we have a function of n in the front of this quantity x minus 3 to the n minus 1. So that means we're going to have to start by applying either the ratio or the root test. Now we'd only apply the root test if everything here is raised to the power of n, and here this n on the top is not raised to the power of n. So we're going to go ahead and apply the ratio test. And let's go ahead and remind ourselves that the ratio test says if we solve the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, if that's less than 1, then we know we have found values that make the series converge. So this is what we're going to set up right now. We want to find all the values that make the series converge. So let's go ahead and try to solve this inequality. So we're going to go ahead and set up the limit as n approaches infinity of the absolute value of a sub n plus 1. So I'm going to replace each n here with n plus 1. Let me go ahead and put a big fraction bar here. So I'm going to replace this n with an n plus 1. And then x minus 3 to the n minus 1, that's all in the numerator. I'm going to replace this n with an n plus 1. So n plus 1 minus 1, well, that's just n. So we're going to have x minus 3 to the n. And in the denominator, 2 to the n is going to become 2 to the n plus 1. So I have replaced each n with an n plus 1, and then we're going to divide by a sub n. So this whole thing is a sub n. If I divide by that, it's like multiplying by the reciprocal. So basically this whole thing, wherever the terms are at, they're going to flip to the opposite side. So this n, instead of being in the numerator, is going to be in the denominator. And then x minus 3 to the n minus 1 is technically in the numerator here because it's like over 1. So that's going to move to the denominator. So we're going to have x minus 3 to the n minus 1. And then 2 to the n's in the denominator, so it's going to move to the numerator. So what we're doing is we're multiplying by the reciprocal all at once here. And we need to know, when is this less than 1? So we're solving, when is this true? Okay, so let's do some rearranging here to kind of see a little bit more of the simplification. I'm going to choose to put n plus 1 above n. So I'm going to kind of keep those similar polynomials next to each other. So n plus 1 over n times, then 2 to the n on top and 2 to the n plus 1 on the bottom. I'm going to write this as 2 to the n on the top, and then 2 to the n times 2 to the 1 on the bottom. So these 2 to the n's will actually cancel. Those are just going to give me a 1. And then on the top, I have x minus 3 to the n. And then on the bottom, I have x minus 3 to the n minus 1. So total, I have one extra copy of x minus 3 on the top. So I have one less copy on the bottom. So this right here is going to simplify, but I'm going to do it on the next line, to just one copy of x minus 3. So what's going to happen now? I have the limit as n approaches infinity so right here I have like a 1/2 left. So I'm going to put that 1/2 and then n plus 1 over n. And then I just have one copy of x minus 3. Because again, there's n copies up here, n minus 1, so one less copy. And so total, I just have one copy because they're going to cancel out, right? So it's kind of like if I have x to the 5th over x to the 4th. So if there's one less copy on the bottom than on the top, total, I just have x left over. So just trying to help understand that simplification there. Okay, so let's make a little space. The limit as n approaches infinity here, well, that applies to this n plus 1 over n. And since they're the same degree, we can go ahead and say that it's just going to be like a 1 over 1 here, but there's a 1/2 in the front. So really, we're just going to have the absolute value of 1/2 times x minus 3 is less than 1. So we evaluated the limit, so the limit is gone and the n um, factors here. And then I can solve this. I can go ahead and pull out the 1/2, and I have 1/2. The absolute value of x minus 3 is less than 1, multiplied by 2. So absolute value of x minus 3 is less than 2. So at this point, I have that x minus a is less than r. So my radius of convergence is 2. And now, if I want to start to find the interval of convergence, I am going to move forward with trying to solve the three-part inequality. So I'm going to have -2 is less than x minus 3 is less than +2. And we'll add 3 to all three parts. So that's going to leave us with 1 is less than x is less than 5. But here's the big difference. We don't know what happens at 1 and at 5, if those are included or not in the interval of convergence. So for the ratio test, when the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, when that equals 1, that didn't tell us anything. We knew nothing. It was inconclusive at any value that made the limit of the ratio equal 1. Well, the value 1 and the value 5 make the limit of the ratio equal 1. So we're not really sure what happens. So these inequality symbols here are not exactly true. Like we don't know for sure. So I'm going to put question mark, question mark. We don't know for sure if this is less than or equal to, if this is less than or equal to. So we have to check what happens at x equals 1 and x equals 5 in the original power series. So we're going to make some more space. Here with that original power series, let's go ahead and attempt to check what happens when x is equal to 1. So if I replace this x right here with a 1, then I'm going to end up with the series, the sum of n equals 1 to infinity, n over 2 to the n. And then 1 minus 3 is -2. So I'm going to have -2 to the n minus 1. So let's attempt to simplify this. I have n equals 1 to infinity, n over 2 to the n. I'm going to split this up. I'm going to make this -1 to the n minus 1, and then 2 to the n minus 1. Or how about 2 to the n times 2 to the -1? Because what I want to do is I want to cancel 2 to the n over 2 to the n. So the series that I'm really looking at is the sum of n equals 1 to infinity of -1 to the n minus 1. So it alternates. But then what I have is n over 2. So 2 to the -1, we would bring that to the bottom. It'd become 2 to the 1. So I really just have n over 2 here. This is going to diverge by the test for divergence. If I consider the limit as n approaches infinity of, let's just say n over 2, well, this is going to go to infinity, right? As I start to plug in big numbers, this is going to get really big. If I put that alternating piece in front, it's just going to flip-flop back and forth between big positive, big negative, big positive, big negative. So this limit does not exist. So that means by the test for divergence, right? So by I'll say the nth term test, the series diverges. And so what does that mean? Well, that means that at x equals 1, that is not included in the interval of convergence. So this is no longer a question mark right here. 1 is not included. So I'm going to come back and erase that and leave it as a less than symbol. Because if something's not included, we would just put less than, not less than, or equal to. All right, so then we have to do the same exact thing for the other side of the interval. Check x equals 5. So I'm going to plug 5 into this x right here and then see what happens. So I'm going to have the sum of n equals 1 to infinity of n over 2 to the n. And then we're going to have 2 to the n minus 1. And it's actually going to give us the same result. So we're going to have n over 2 to the n. Then we're going to have 2 to the n times 2 to the -1. The 2 to the n's are going to cancel. So I have, instead of alternating this time, I just have n over 2. And so if we take the limit as n approaches infinity of n over 2, that's infinity, right? Which is not 0. And so by the nth term test, this series diverges as well. So because both endpoints led to an infinite series, not a power series anymore, just a regular old infinite series that diverged, that means that the corresponding endpoints are not included. So if they did converge, then we would include that particular endpoint. But as it stands, we are not going to. So the interval of convergence is just uh, 1 is less than x is less than 5, or if we want to write it in interval notation, we would say 1, 5 with open parentheses around both values. Here, let's find the radius and interval of convergence of the sum of n equals 0 to infinity, negative 1 to the n, x to the 2n, all over 4 to the n times n factorial squared. So this one is also not geometric. So the c sub n is going to be negative 1 to the n over 4 to the n factorial squared. And that's definitely not a constant. So we're going to move forward with using the ratio test. We're not going to use a root test because n factorial squared doesn't have an n up in the exponent. So we're going to go ahead and attempt to solve the limit of that ratio. The limit as n approaches infinity of the absolute value of, I'm going to put like a big fraction bar. So we're going to replace every n with n plus 1. So negative 1 to the n plus 1. And then here I'm going to replace n with n plus 1, which is going to create x to the 2n plus 2, because n plus 1 would get multiplied by 2. So both the n and the 1, which creates an exponent of 2n plus 2. In the denominator, there's going to be a 4 to the n plus 1. And then we're going to have n plus 1 factorial squared. So I'm going to have n plus 1 factorial, but squared, 2 copies of that. And then technically we divide by a sub n. So here this whole thing is a sub n, but instead of dividing by a sub n, I'm going to multiply by the reciprocal. So I'm going to take everything in the denominator and put it in the numerator. So that's going to be 4 to the n and then n factorial squared. And everything in the numerator, I'm going to put that in the denominator. So that's negative 1 to the n, x to the 2n. And the ratio test says that this has to be less than 1 in order to converge. So now let's rearrange things and clean this up a little bit. So I'm going to have the limit as n approaches infinity. Well, these absolute value bars are going to make these alternating factors go away. We're not going to deal with those at all. Let's go ahead and look at the exponential pieces. 4 to the n over 4 to the n plus 1. I'm going to go ahead and put 4 to the n over 4 to the n times 4 to the 1. Then let's look at these factorial pieces. So on the top, I have an n factorial and another n factorial, because n factorial squared. On the bottom, n plus 1 factorial squared. So I have 2 copies of this as well. And I'm going to choose to write it as n plus 1 times n factorial and n plus 1 times n factorial. So there's each copy of n plus 1 factorial with just n plus 1 peeled off so that I can cancel out the n factorials. And then x to the 2n plus 2, I'm going to rewrite that in the numerator as x to the 2n times x squared, and then I have x to the 2n in the denominator. So I'm choosing to just write everything out so we could really see how things are going to simplify here, how the 4 to the n's are going to cancel, the n factorials are going to cancel, leaving me with just 2 copies of n plus 1 on the bottom. And then the x to the 2n's are going to cancel as well. So let's see what we have left. We're going to evaluate this limit as n approaches infinity of, let's see, we're going to have 1 over 4. We're going to have n plus 1 squared. So I have 2 copies of n plus 1. And then I'm going to have an x squared there. When is that less than 1? Well, this one's interesting. As n approaches infinity, if I focus on this 1 over 4 times the quantity n plus 1 squared, that's going to go to 0. The top's constant, the bottom is getting really big. So this is all going to 0. So what I have is 0 times x squared is less than 1. Let's make a little bit of space here. So in this case, it doesn't matter what I plug in for x, anything times 0 is still going to give me 0. So I'm always going to end up with 0 is less than 1. This is always a true statement. Always, as for any x value. For any x value we plug in, we're always going to get a true statement. 0 is less than 1. So what does that mean? It means that the interval of convergence, what x values make this series converge? All x values. So the interval of convergence is negative infinity to infinity, and the radius of convergence is infinity. So it's a really nice special case that happens because we ended up with this true statement, right? Always true for any x value. Let's find the radius and interval of convergence of the sum of n equals 1 to infinity of cosine of pi n times n factorial to the n, x to the n, over n to the n. So for this one, we are going to use the root test. This is definitely not geometric. And here we have everything is raised to this nth power here. Let's go ahead and set up our root test. So we're going to go ahead and solve the limit as n approaches infinity of the nth root of the absolute value of this term. So we're going to have cosine of pi n, n factorial to the n, x to the n, all over n to the n. So cosine of pi n is actually an alternating factor. It's like the same as negative 1 to the n or negative 1 to the n plus 1. So here, cosine of pi n is alternating between positive 1, negative 1, positive 1, negative 1. So I can basically just ignore it because those absolute value bars are right there, and they're going to make any negative a positive. So what I need is this is less than 1, right? We're solving for when this is less than 1. It's the same conclusion as the ratio test. So this next line right here is going to be the limit as n approaches infinity. I'm going to keep those absolute value bars. And what I'm going to do is apply the nth root to each of these that are raised to the n. So basically the nth power is going to disappear because of the nth root. And the cosine pi n is going to be gone because the absolute value bars get rid of it. It's like an alternating factor. So what we're going to be left with is just n factorial x over n. When is this less than 1? So we're trying to think about the limit as n approaches infinity of n factorial over n. Well, n factorial is definitely growing really, really fast compared to just n. So this piece right here is infinity. So we're looking at like infinity times x. When is this less than 1? Well, it's not, right? It doesn't matter what we substitute in for x right here. If we're multiplying it times infinity, that's never going to be less than 1. So here, never, right? This is never true. This is always a false statement. And so what do we say about the radius and the interval of convergence? Well, the radius of convergence is just 0. So the radius of convergence is 0. And then the interval of convergence is a single number. The interval of convergence is whatever the center is, whatever the center of the power series is. So let's go back up to the power series for a second. We have x minus 0 to the n. So this piece right here, we can think of as x minus 0 to the n. So the center is 0. So every power series converges at its center. So the way we're going to write that is just 0 in like these squiggly braces. So this is a set of numbers, except it only includes one number, and that number is the center, which happens to be 0. So this is kind of the bad case, that the radius of convergence is 0 because the interval of convergence is the center only. Now let's try to summarize the radius and interval of convergence types. There are 3 possibilities for the radius of convergence. First, r could be equal to 0. That's the bad case, where the power series only converges at its center. The second possibility is that the radius is infinity. That's the best case scenario. The radius of convergence is infinite, so the series converges for all x values. Or the radius of convergence could be a positive finite number. In this case, the series converges for all x values that satisfies the absolute value of x minus a is less than r. Now, of course, we can solve that inequality and get this interval a minus r is less than x is less than a plus r. So it's going to converge within that interval and diverge outside the interval. To determine what happens when the absolute value of x minus a equals r, so those are the endpoints being created, we must test what happens at the endpoints of the interval. Unless it's a geometric power series, then we don't have to test the endpoints. They are just not included. So the interval of convergence could be any of the following. It could be a totally open interval. So here both sides have parentheses. It could have one side be open and the other side be closed, like the next two examples, or it could be a fully closed interval, so brackets on both sides of the interval. Here's the main idea. If our power series is not geometric, we must use the ratio or the root test to find the radius of convergence r and test the endpoints to find the interval of convergence if r is not 0 or r is not infinity. So now what we're going to do is learn more tests to check the endpoints of the interval of convergence.